Well, thank you all for coming to Wednesday night 11 night. I'm Thompson. I work at the Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H, and on behalf of those folks, come to Wednesday night lab. It's also co-sponsored by the Wisconsin Alumni Association, PBS Wisconsin, and the Madison Science Alliance. And again, thanks for coming. This is our second return. Last week was a special one for Ice Cube, and I'm glad to be back here on a team basis now. Next week, we're going to have Steph Ty from the law school, and they'll be talking about their work in using legal approaches to protecting culinary heritage, especially in the face of climate change. And then Benjamin Zuckerberg will be here in 2 weeks. He's with the Department of Forest and Wildlife Ecology, and we'll be talking about how birds are sentinels for climate change and how they're adapting. How's that sounding, Chris? Good? Okay. It looks absolutely perfect. Right, so that's a little stretch. And then tonight, delighted to have Christy Remucal back from the Department of Civil and Environmental Engineering. Here's second. And she'll be talking with us about PFAS, other affecting waters in Wisconsin. I'm going to ask you the 5 questions that there's not tradition of asking folks. Where were you born?
I was born in Prescott, Arizona.
Prescott? Wow. And where'd you go to high school?
In Taos, New Mexico.
You went to school at high school in Taos?
Yeah, I grew up there.
We visited there last August 2020. And then where'd you go for your undergrad?
I went to MIT.
And where'd you study?
Environmental engineering.
And where'd you go for your advanced degrees and what did you study?
Civil and environmental engineering, and I went to UC Berkeley.
And then I understand you were in Switzerland for a while?
Yep, I did. I was there for about 3 years for a postdoc, and then we went back in 2018, 2019 for a sabbatical.
And what town was that?
In Zurich.
So it's my pleasure to welcome Christy back to Wednesday Night Lab. Please join me. Welcome.
Great. Thanks, Tom, for the invitation to be here. And thank you all for coming out tonight, whether you're on Zoom or here in person. It's really nice to be here. And thank you all for your patience as we've dealt with all the hybrid world. I know with teaching, it's like doing it in person, recording, it's like a lot of work, getting it all to work. So thanks everyone for the team for getting us all set up. So in my talk tonight, I'm going to present some of our work going on PFAS, or per and polyfluoroalkyl substances, here in Wisconsin in our surface waters. So that's what we're going to cover. I think many of you are maybe here or interested in this because you've seen these chemicals in the news. So I wanted to start by just sharing some headlines that have recently for here in Wisconsin. Sorry, let me make that go away. So this is a recent headline from French Island in La Crosse. Residents there are drinking bottled water because of PFAS contamination. The town of Peshtigo is dealing with a lot of PFAS issues in their water. This is a big problem. We work a little bit in that area, so I'll talk more about this area. Down here in Madison, we have a fish advisory in Lake Monona and some of the downstream waters for PFAS in our fish. PFAS have been found in deer livers in the state, and then in pretty high concentrations in foams that form naturally on the surface of our waters. So these are just a few headlines. There's a lot of them. If you pay attention to the news here, you see PFAS in the news a lot. And so what I want to talk about today I'm just going to start with the beginning. What are these chemicals and why do we care about them? Why are they getting so much attention in the media, in research, in regulation? Like why are they such a big deal? And I'll try to put this in perspective of these chemicals versus other chemicals you might have heard about before. They have some special properties that make them especially problematic. And then I'll get into some of my work talking about PFAS in the Great Lakes, looking at how their concentrations vary as we move across the 5 Great Lakes. And then I'm going to present some really new work that's not quite out yet, but it's looking at PFAS around Green Bay in the rivers in that area. And then after I've told you all these scary things about the chemicals, I'm going to talk just a little bit about like treatment options. Yeah, just what's available there. So I want to start with some definitions. One thing that is really challenging with, speaking about these chemicals or talking about them is that it's like alphabet soup. There are really long acronyms and it's a little bit hard to get your head around. So I'm going to try to keep it as simple as possible. And I'm going to just sort of get us started. So PFAS, sometimes pronounced PFAS or PFASs. This stands for per and polyfluoroalkyl substances. This is a catch-all term that describes all of the chemicals that are in this class of chemicals. We don't actually know how many PFAS there are. We think about 5,000, but every time I see an estimate, that number keeps getting higher. A few years ago, it was 3,000. We don't know how many there are. But I'm going to use the term PFAS to describe this class of chemicals in general. Now, PFOS, which you might see a lot in the news, this is one of these 5,000 plus chemicals. It gets a lot of attention for a lot of good reasons, which I'll get into, but this is one specific chemical. It used to be in Scotchgard, if you remember that from like stain sticking things. It's listed as a persistent organic pollutant. It's actually not made or used in the US anymore, but it sticks around for a really long time and it's prevalent everywhere in our environment. The other chemical that also gets a lot of attention is PFOA. This was formerly used to make Teflon. So think about your nonstick pans, things like that. It's also been phased out here in the US, but again, we have this legacy of these chemicals in our environment. And so, yeah, these two are driving a lot of the regulations. So we hear about them a lot. So again, to recap, PFAS is everything, and then I'll spell out the letters for the other ones, and I'm talking about just one chemical. But yeah, it's alphabet soup as it goes. So what are these chemicals? Like I said, there are over 5,000 different PFAS that we know about, and they're used in a lot of different applications. So anything to make things non-stick or waterproof or grease resistant. So your non-stick pan, your microwavable popcorn bag, any stain resistant carpet, your Gore-Tex rain jacket, all these things that repel water or grease probably have PFAS in them. They're used in a lot of industrial applications. Chrome plating is a nice example. And then they're also used in a lot of firefighting foams. And this has really led to a lot of environmental contamination in particular. A little bit of a history, even though PFAS are getting a lot of attention right now, and they're sometimes even called emerging contaminants, they've been around for a really long time. So PFOS and PFOA, the two that I introduced that are getting a lot of attention, they were made in the 1940s. So they've been used for a very long time. And again, you can see here, we're not really using those chemicals anymore, but we're using other PFAS instead. Shorter chain compounds, slightly different structures. We're still using plenty of PFAS. We're just not using those two. So they've been around for a very long time. So why we care about them, of course, one of the major reasons is because they have some adverse health outcomes. So some of these 5,000 chemicals, we know some of their health outcomes. And so some of these individual chemicals have been linked to things like thyroid disease, fertility issues, decreased immune response, increased cholesterol, and in some cases, usually with like high occupational exposure, even cancers. So those are not good things. Another thing that's concerning about these chemicals is that some of them bioaccumulate. And so that means that once they're in your body or once they're in your the food chain, they kind of stay there and their concentrations increase. Some chemicals like PFOS bioaccumulate like in fish, and that's why we have fish advisories for these chemicals. And another thing that makes these chemicals a little different than others is that these health effects happen at very low concentrations. So just to put things in perspective, the regulation that's being proposed for groundwater here in Wisconsin is these two chemicals, PFOS and PFOA, at 20 nanograms per liter, which is parts per trillion. Arsenic, which you might think of as being a poison, is allowed to be 500 times higher concentration in our water. So another reason why these chemicals are getting so much attention is like, we're able to measure them at these concentrations in the environment. That these are really low levels. It's hard to do like in the lab, but we now have the capability to measure them. So how do PFAS get into the environment? So I'm an environmental chemist, and I study how these chemicals move around the environment. So just to sort of set the stage, there's a lot of ways we can get these chemicals into our environment. You know, you might think about wastewater, leaving an industry that's using PFAS, that might be sent to a wastewater treatment plant. Same thing with landfill leachate that might have some of our consumer products in it. That might also end up at a wastewater treatment plant here in the middle. Wastewater treatment plants are not a source of PFAS, but they're also not designed to remove these chemicals. And so that means that in general, any PFAS that come in go out the other end. Some of that may end up in the water, where here in Wisconsin, they're going to usually be discharged to a surface water like a river. That's where our wastewater goes. And some of the PFAS may end up in the solids. You know, we could have sludge that's being that's being sent back to the landfill, and that just kind of goes around in a circle. Or what's commonly done in Wisconsin is the biosolids are land applied and used for fertilizer. And this is really great because we're recycling, you know, nutrients and energy, and it's a free source of fertilizer. But if it has PFAS in it, that's a problem. There's other sources as well. A really big one are aqueous film forming foams, AFFF. These are firefighting foams that contain PFAS. When these are used either for training or used to fight a fire, and they're not contained, that's a really easy way to get a lot of PFAS out into the environment. So you'll see when I show you some sites in a little bit, a lot of the sites in Wisconsin are associated with firefighting foam use, either at the military or a lot of airports, because they have to keep these really powerful fire retardants at the airport in case of a fire. So we'll see a lot of themes of airports and military contamination. Another thing that we're learning about is we actually have PFAS in our precipitation, which is kind of crazy to think about. The National Atmospheric Deposition Program is based here at the Wisconsin State Lab of Hygiene, and they're measuring PFAS in precipitation. You know, again, low levels, but it is there. And this is it rains everywhere. So this is a way of spreading these chemicals further throughout our environment. So what happens to them? This is PFOS, and I put this up here. I know, yeah, it's a sort of general audience talk, but I had to put the structure up here to sort of explain how someone like me, who's an environmental chemist, can look at this structure and, you know, it raises some red flags. So there are three things about this chemical that are concerning. First, this long carbon backbone, all these points here, those are carbons. This is going to make this chemical lipophilic, or it's going to help it accumulate or build up in biota, like living things like fish, or sediments, like at the bottom of a river or a lake. The longer this carbon chain is, the more likely it is to sort of stick to surfaces. But the thing that's unique about PFAS is that the other end of the chemical, they have this, in this case, something with a negative charge, a sulfonate group. This helps it dissolve in water. And so these chemicals are really unique because they have this sort of dual nature. One part is, you know, liking surfaces and solids, and one part is liking water. So they kind of, you know, polar opposite regions. This is sort of, this dual nature is why they're so attractive for all these industrial and consumer applications. But it's problematic because once these chemicals are out in the environment, they can end up everywhere. Because they dissolve freely in water, they can move anywhere that the water goes. But we also need to think about them in fish, in our sediments, and everywhere. So yeah, that's a little concerning. The other thing that jumps out maybe are all these Fs. Those are fluorines. The carbon-fluorine bond is one of the strongest bonds you can have in an organic chemical. And you can see something like PFOS has a lot of these bonds. They're very hard to break down. And this is one reason why these chemicals are sometimes called forever chemicals. That's, if you see it in the news, that's why. Something like PFAS does not have any known natural degradation process pathways. We don't know how long it lasts. So these chemicals move freely in the environment, they last a really long time, and they have adverse health outcomes. And so altogether, yeah, a lot of red flags, and that's one reason, those are reasons why they get so much attention. So where are they found? You know, given that they've been used for decades, they move around, they don't really break down, it's perhaps not a surprise that we find them all over the place. This is a map from the Environmental Working Group. They update it periodically. Every point on here is a site where there's been PFAS detected. You see a lot of blue, those are drinking water. We often think about PFAS as a groundwater contaminant, although, yeah, I'll show you, it's a surface water contaminant as well. And then the purple, those are military sites where they've used these firefighting foams in general. Now, there are a few states on this map that jump out at you, right? Like Michigan, Colorado, New Jersey. Why do they have so many dots? It doesn't mean that they have more PFAS contamination. It just means that they have been looking for it. So a state like Michigan is ahead of where we are in terms of testing all around their state. And they're finding more PFAS everywhere. So some of these states that have a lot of dots have just been looking for it more. Every time you look at this map, there are more dots on it. Here in Wisconsin, this is a map from the Department of Natural Resources that they put out in May. And yeah, you can see sites where the DNR has detected PFAS. And I just highlighted a few. French Island and La Crosse, this is on an airport. So thinking about the firefighting foam use on an airport, some National Guard bases. You know, here in Madison, you've probably heard about Starkweather Creek, which we think is probably impacted by the airport. That has high PFAS in it. Lake Monona downstream is elevated because of that. So yeah, a lot of military airport sort of associations. And then one of the places where we're working is up here in Marinette, right here at the border of Michigan. And this is a little bit different. It's home to the Tyco Fire Products facility where they've made and tested firefighting foams for a long time. And there is extensive groundwater contamination in this region, and which I'll get to in a minute, we're looking at what that means for surface waters. But this is a pretty big, the Marinette region is a pretty big hotspot for PFAS in the state. Okay, so this is a little bit scary, right? I just told you all these bad things, and I probably have convinced you that these are things we need to pay attention to. What's being done? At the federal level, it's been slow, I think is a nice way to put it. There's not a lot going on at the federal level yet. The EPA issued a health advisory level for, again, these two chemicals, the two that we often focus on first, PFOS and PFOA, of 70 nanograms per liter. This is just an advisory level. This means that, hey, if you have this much PFAS in your water, you should maybe do something about it. But it's not a rule that drinking water utilities have to address it. It's not a regulation. It's just a suggestion. So states are really taking this into their own hands. And it's kind of all over the place, and it's happening at different paces, but states are slowly coming up with their own enforceable standards. And so the states that are highlighted here are ones that had standards on the books as of January that were enforceable. The ones in orange are ones that had limits that are lower than the 70 nanograms per liter. The ones in blue are at that 70 level. And then I don't know what North Carolina is doing. They're actually above 70, but you can see there are differences across states. Plenty of states don't have regulations yet. What about here in Wisconsin? Wisconsin has a groundwater standard that's going through the rulemaking process of 20, so lower than that, the EPA advisory level. This is in line with a lot of other states. And we're also considering regulations for 16 other PFAS, again, out of these like 5,000 plus chemicals, ones that we know their health impacts for. The rulemaking process takes about 3 years. So they're going through the process. We'll get there eventually. We'll be colored on this map eventually, but it takes time. That's for groundwater. There's also a surface water criteria that's also going through the process. And you can see the concentrations are a bit different. it's lower for PFOS, and that's because this is a chemical I'll show you that we often find in fish, and this is driving a lot of the fish advisories for PFAS. It's really just this one chemical. And then you can see for PFOA, it's 20 nanograms per liter for in public water supplies. That means if people are drinking the water, and 95 for other surface waters. So there's a lot of work going on with coming up with regulations here in the state and elsewhere. There's a lot of other state efforts. It's been really amazing to see over the past 2, maybe 3 years now, how much attention these chemicals are getting. So the Department of Natural Resources and the Department of Health Services are really working across their agencies to develop standards, doing monitoring, source identification. And I listed this website and I'll put it up at the very end. We could talk for an hour about all the different things that they're doing and the different initiatives. Like they're really doing a lot of different things, but that's a great resource if you're interested in finding out more. Another sort of interesting thing is this Wisconsin PFAS Action Council. This was created through Executive Order 40, and it has representatives from 17 different state agencies. I'm the university representative on that committee. We've been working, gosh, it's hard with the pandemic, it kind of messes things up, but we've been working for almost, a year and a half, 2 years. And it's kind of amazing to see how all these different agencies, how PFAS touches them in some way, like agencies you wouldn't even think of. But we worked together and we submitted an action plan to the governor in December of 2020. And it touches on these 4 areas on the right. So how do we prevent future contamination? How do we even find out the scope of contamination in the state right now? What do we do about it? And then how do we educate and communicate about the risks associated with these compounds? So that's also available online. There's a lot of really good ideas in there, and some of them we're making progress on actually doing those. So that's been a really interesting process to be part of. Okay, so let's get to some research. So my group is focusing on the fate of these chemicals in surface waters. We're focusing on the Great Lakes. One of the reasons for that is, we're here in the Great Lakes, but the Great Lakes are really important. They provide drinking water for over 40 million people and support really important fisheries. And they're huge. The sources of PFAS to these lakes are really dispersed, not well characterized. And in particular, which I'll show you some data on, there's not a lot of information out there on Lake Michigan. So that's one of the reasons why we're focusing there, especially because there are known sources like the Marinette region, which are sources of PFAS to the lake. So let me show you some results. So when I started working on this, one of the things that I did was do sort of a data synthesis of like everything that was out there. What did we even know? So I want to show you, we're going to look across the 5 Great Lakes first, and then we'll dive into Green Bay. What do we know? So these are measurements of PFOS. Again, that's like one of the ones that we talk about a lot. It's kind of one of the bad actors. Its concentrations in Lake Superior, Michigan, Huron, Erie, and Ontario. So all the figures I'm going to show for a minute, we're going to move from west to east across the Great Lakes. You can see that the concentrations go up as we move from west to east, right? So Superior, things are looking pretty good. Erie and Ontario, concentrations are higher. Although, just to point this out, they're still below that 8 nanogram per liter surface water criteria that's proposed. PFOA, the other one that drives a lot of the regulations, again, it sort of increases from west to east. Concentrations are a little bit lower than PFOS, but similar. So we see this a lot, this increase from west to east. We also see, if you look, each of these dots is an individual study that was available at the time when I was putting this data together. And there's a lot for like Ontario, but there's really only a couple studies in Lake Michigan. So that's one reason why I want to work and learn more about it. Looking at other chemicals, this is sort of a synthesis of all the water data that's available for the Great Lakes. Again, you can see, it even took me a long time to learn what all these different letters correspond to. That's kind of complicated. It makes sense to me now, but there's a lot to kind of get your head around. So the warmer colors are ones that are in the same class as PFOS, and the cooler colors are in the same class as PFOA. And we're basically going from shorter compounds to ones that are longer, thinking about that long carbon backbone. So we can see that the concentrations of these commonly studied PFAS also increase from west to east. It's not just PFOS and PFOA. Now, I mentioned at the beginning, one thing that's sort of challenging about these chemicals is they don't just stay in the water. They also go to the sediment and they also go to biota. So what do we know about sediment concentrations? When we think about a chemical in the environment, we think about this idea of partitioning, where it goes from the water to the sediment, and this is governed by this equilibrium constant. Every chemical has a value for this. They're all going to be a little bit different, but it's going to tell you relatively how much is going to be in the water versus how much is going to be in the sediment. The structure matters. The longer that carbon chain is, the more likely it is to stick to the sediment. And also the other side of the chemical matters too. Something with a sulfonate like PFOS is more likely to sorb to or stick to the sediment than PFOA. So that's kind of what we would expect. So when we go to the sediments, here's our water data that I already showed, and here's our sediment data. You can see that increase from west to east again. You can see there's a lot of different colors on here. That's kind of what all I want you to get to take away from this is we have a lot of different colors than we see over here. Basically what we're seeing is that we're seeing a lot of orange, that's our PFOS again. And we're seeing a lot of these longer chain carboxylates, the same class as PFOA. Some of these long ones have, 13, 14 carbons in them. We don't even see them in the water at all. So we're seeing a lot more longer chain compounds in the sediment, and that's kind of consistent with our idea of how these chemicals would move in the environment. So their sort of fingerprint is going to be different whether we're in the water or the sediment. One other thing that's really interesting is, we can do experiments in the lab and predict what this ratio should be, but what we find in the environment doesn't match that. We actually find a lot more in the sediment than we would predict based on our laboratory measurements, which is kind of interesting. So PFAS can sort of stick to the sediment, but they can also go to fish and birds and other things. It's the same idea. Longer chain compounds are going to be more likely to be found in fish. Sulfonates more likely than the carboxylates. Same idea. And so that's what we see. So this is data for lake trout. Again, across all the Great Lakes. You see a lot of orange on there. That's PFOS. That's the compound that's driving a lot of the fish consumption advisories here in Wisconsin. So again, more PFAS in general in the Eastern Lakes, and we find a lot of PFOS. Now here I put for you the advisory from the Great Lakes Consortium for Fish Consumption. And we're in this 50 to 200 we're below that, but this is just kind of putting that in perspective. Sorry. Units, microgram per kilogram and nanogram per gram are the same thing. So we're in this 50 to 200 range, which is like a 1 meal per month in some of these Eastern lakes. And the data is similar for birds in the Great Lakes as well. So we see a lot of consistency where, concentrations, whether we're looking at water or sediment or fish, are higher in Erie and Ontario compared to Lake Superior. And we see differences whether we're looking at water or fish or sediment, and that just has to do with how these chemicals move. We learned a few things from this. At Lake Michigan, there's not a lot of data. How much goes into the sediment doesn't match what we see in the lab. And we also don't know a lot about the sort of newer PFAS that are being used. So I want to share with you now a study that we've been doing that's in review right now, that's maybe a little bit closer to home and with data measurements that we're doing in our lab. And we're focusing a lot around Green Bay. In particular, we're really interested in the Marinette and Peshtigo region, which again is up at the border of Wisconsin and the Upper Peninsula of Michigan. And that's in part because of this fire products facility, which has made and tested these firefighting foams for a long time. And I think, they would test these foams and then just wash them off into the environment. And it's not a surprise, there's a lot of groundwater contamination in that region. So the facility, they have where the stars are on this map, this is where they're located. There's a lot of private groundwater wells that are contaminated in this region. The groundwater kind of moves in this direction to the bay. So we're thinking about what does that mean for surface waters. We're also interested in biosolids. So up until about 2017, the biosolids from the wastewater treatment plant in this area was applied to fields. And so you think, okay, the PFAS leave like this industrial facility, they end up in the biosolids of the treatment plant, and then they get spread at all the fields all around. So we're also doing a little bit of work up in biosolids impacted fields. There are other potential sites of interest. So yeah, the biosolid fields I just mentioned. The city of Green Bay, of course, has an industrial legacy. And so there are lots of potential sources there. And then airports because of the use of firefighting foams. And so what we were trying to do in this study was really figure out some of the sources of PFAS around the bay, and then also think about how these chemicals move in the environment. Again, with the idea that what we see in the field doesn't match what we see in the lab. And so what we did was we went and sampled 39 different sites all around the Bay of Green Bay, including all the major tributaries. And you can sort of see all the dots there. We wanted to identify and characterize different hotspots around the bay. We also wanted to quantify loadings. How much PFAS are these different rivers putting into Lake Michigan? And so those are some of the aims of the study. We measured 10 different compounds, which is not a lot in that group of 5,000 chemicals, but we picked the ones that we work a lot with the DNR on this project. So we picked ones that they were finding in their measurements, and also ones that are driving a lot of the regulations. All right, so let me show you, before I get to the data, I want to talk a little bit about how you measure these chemicals, because it's not easy. It is not easy because we're talking low concentrations and you have to be super careful. If you send a sample to like the state lab to be analyzed, it's like hundreds of dollars per sample kind of range. So I'll tell you a little bit about how it works, because yeah, you have to be careful and it's expensive. So first we actually add isotopes, like so PFOS, but with like a carbon-13 instead of a carbon-12, so we can kind of account for any losses in our processing. So we have to add those, and then we extract our sample. We basically take it from like 250 milliliters down to 1. And then we analyze it by LCMS, liquid chromatography tandem mass spectrometry. This part in the middle is actually like the one part that takes the most time and effort. So this is always our bottleneck in doing this analysis, but it's not trivial. These things are hard to measure. All right, so what do we have? So I'm going to show you a few figures that look like this, where we go clockwise around the Bay of Green Bay. So we're going to start in Door County, go to the city of Green Bay, and then kind of keep going around till we get to the Marinette region. And then we get into the UP, the Upper Peninsula of Michigan. Again, you can see there's our long list of different chemicals. You don't need to worry about them, just the heights of the different bars. One thing jumps out at you. This one here, ditch B, is really, really high compared to the others. This actually drains directly off the Tyco facility. This wasn't active at the time, but they have like a treatment system on that ditch now that's like treating the ditch water to clean it, because yeah, DNR knows about this. That has a lot of PFAS in it. That sort of outlier aside, there's some variability. Some are really low, like up in Door County, 4 nanograms per liter. That's, we're really pushing our detection limits with some of these measurements. And other ones are lower than we thought. The Menominee River, the Peshtigo River, sort of, in Marinette and Peshtigo, they don't really jump out at you. Nothing really is too dramatic otherwise. And one of the things is thinking about what all this means for regulation. So the proposed surface water criteria for Wisconsin are there again. And this was actually only exceeded by ditch B, the one that was really, really high. And so this tells us that if we're focusing on sites with high concentrations, in some ways that makes sense. Like if you're thinking about human exposure, like people swimming in that water, or the ecosystem, the fish in that water, or like your kids or your dog playing in that water, you wouldn't want to be in ditch B. That's not good. But what if our goal is to prevent PFAS from entering the Great Lakes? Is this idea of just focusing on the hotspots the way to go? So, I'm an engineering background, so I did a mass balance. And basically what we did was we took that concentration in water that we measured and we multiplied it by the discharge or the flow rate, like how much water, basically how big are these rivers? And we see a different story. So on the top, this shows the water concentration that I showed before, same data. And on the bottom is the loading, how many grams per day these different rivers are putting into Green Bay. And you can see just by eye, they look different, right? They don't match up. And so it turns out the really big rivers are putting in most of the PFAS. So, the Fox River, it's kind of small. Its concentration is not a big deal, but it's putting in the majority of the PFAS, or it's the highest contributor. And then we have the Menominee and Peshtigo, again, sort of modest aqueous concentrations, nothing that jumps out at you. But when we do a mass balance, they're actually putting in these three rivers 2/3 of the PFAS that's going into the Bay of Green Bay. Ditch B, which had this, really jumped out at you in this other figure, it's the mass it's putting in is pretty modest actually. So if we're at the perspective of like wanting to protect the Bay or wanting to protect the whole of Lake Michigan, we need to think about some of these bigger rivers, even if their concentration on its own isn't so high. Sediment concentrations, moving to sediment, we focused on this in part because the DNR wasn't doing sediment measurements. And so it was really nice to work with them and have our work really complement the efforts that they're doing in some of these sites. We find a huge range. So I'm showing the water concentration again, just for comparison. And then here's our sediments. Again, you can see just the pattern by eye looks really different. We see a lot of purple, which in this case is PFOS. It's, the more sticky one. And we find high concentrations in sites near airports and also in some of these sites near biosolids fields. So even though they haven't applied biosolids from Marinette and Peshtigo for several years, we can still see sort of the signature of it in the rivers adjacent to these fields. So again, these chemicals last a very long time in the environment. So we still see a lot of this PFOS, this is legacy compounds. So looking at that ratio between what's in the sediment and what's in the water, one thing we found is that there's about 10 times more of these chemicals in the sediment than what we would expect in the water, which is like a lot. And this agrees with past observations. Other people have seen this as well. I'll sort of skip that long table, but this made us wonder why. Why do we find more of these chemicals in the sediment than we would predict based on our laboratory experiments? So the one thing we asked is, are the sediments at equilibrium? This idea of, a chemical being in the water versus sediments, like things kind of have to be equilibrated or like mixed up for a long time. And so, river, things are moving, like maybe things just aren't at equilibrium because it's like a dynamic moving system. So what we did was we took sediment from a site and then we put water from that same site and we shook it for about 10 days, just to sort of see, like, do things kind of even out after a while. And if we look just to see what happened in the sediment, for example, in this case, a bunch of the sediments lost PFOS and some of the other compounds. So they're getting closer to equilibrium, what we would expect. But in other cases, the concentration went up. And so we took this to mean that, yeah, we're not at equilibrium, but we can't really explain why. Like, why do some sites go up? Why do some sites go down? It doesn't follow our lab experiments. I think we still cannot explain it. But these chemicals they don't behave very well. They don't follow the rules, I think is kind of how it goes. But this made us ask some questions. Like, some of these cases, when we let the sediment sit there in water for a long time, it loses a lot of PFAS. And so that made us ask, like, if these sediments are contaminated and the water was cleaned up, like, would these sediments potentially be a source of PFAS? And thinking about, like, how do we clean up or remediate the environment? And so we did another experiment where we took sediments and then we put Lake Michigan water, which has relatively low concentrations. And we wanted to see would the PFAS come back out of the sediment? And they do. So a lot of negative numbers here. This means, for PFOS and PFOA, a lot of this, they come out of the sediment again if you clean up the water. And so this has some implications for remediation. Thinking about, if we're able to stop PFAS getting into our river, we still need to think about the PFAS that are left over in the sediment because they're not going to stay there. And this is something that's really different than chemicals like PCBs, which you may have heard of, that are really, really sticky and really stay in the sediment. These chemicals, it just really speaks to their dynamic nature. We need to think about the water and the sediment when we're thinking about remediation. So some conclusions from the Green Bay work, and then I'm gonna try to end on a little bit of a lighter note. I feel like whenever I talk about this stuff, it's kind of a bit of a downer. So I'll try to end a little bit lighter, but to wrap up some of this ongoing work, we do see that groundwater contamination associated with firefighting, foam manufacture, and testing has definitely impacted surface waters and sediments in the Green Bay and Marinette region. Thinking about implications for regulations, we need to think about big rivers, not just ones that have high concentrations of the chemicals, because they're putting in the most PFAS to Lake Michigan. And then thinking about the sediment, we need to think about that when we're thinking about remediation efforts. All right, so now that I have made you all worry, like the question you're wondering, like, oh gosh, what do I do? Do I have PFAS in my water? Well, you can find out. If you live here in Madison, you can actually go to the water utility website and find out. Our utility has been really proactive about testing for these chemicals and putting that data publicly available, which they're not required to do it. I think it's great that they're putting that information out there. So for myself, I put in my address. You can find out, my house is served by these three different wells. And then I can go and look up like, okay, they have, 1, 2 nanograms per liter of these two chemicals. So I can go and find that out. And again, the proposed regulation for groundwater is 20. So I'm about 10 times less than that. So like, okay, that's good to know. Looking across the whole city, this is 2019 data. I couldn't find, they have more recent data, but I couldn't find a more recent map. Some of the sites, the ones in green, were basically below detection. The sort of square, I'm not even sure what color that is, had trace levels, like these are the wells. I live on the west side over there. And then a couple wells had what they call low levels. Well 15 was in the news quite a bit a few years ago. They took that offline because of PFAS. It had levels around 9 to 12 nanograms per liter, which is still below that 20 nanogram per liter level. But that one is offline for that reason. Like I said, you can go look it up. Now, what can we do if we have PFAS in our water? There are some existing technologies to remove these chemicals. Granular activated carbon is one that's used most common because it's the least expensive. So like that ditch B, they're actually running it through a granular activated carbon treatment unit, like all the water in the ditch, running it through one of these things. This is basically like what's in a Brita filter, like that same sort of thing. And it's again, that idea of partitioning or sorption. So it's like basically taking the chemical from the water and sticking it to this carbon solid material. Kind of the same idea as in sediment, but just a lot more goes on the carbon than sediment. Reverse osmosis, this is basically running things through a really, really tight membrane. RO takes out like everything, salts and everything. It works really well. It's really expensive and energy intensive. So these are more like drinking water treatment plant levels. At the home, there are point of use filters, either based on sort of technology like activated carbon. You can also get in-home RO. In my house, we have a filter that's sort of based on like this. It's actually just because we don't like the taste of chlorine that we drink filtered water, but we did pick a filter that's been tested to remove PFAS because why not? But those things work and exist. But the thing that's challenging is that neither of these technologies destroy the chemical. They just take it from the water into something else. So the PFAS are still there. And this is actually a really huge area of research right now. None of our usual tricks for destroying chemicals in water treatment work on these chemicals. They are really, really hard to break down because of their chemical nature. And so there's a lot of work going on right now to develop better ways for chemical destruction. So they're getting a lot of attention for good reasons. They're tricky. Okay, so with that, hopefully that gives you some good ideas. Again, I thank you for your attention. I want to thank our funders, Wisconsin Sea Grant, and we work closely with the DNR and the state lab on a lot of this work, and it's been really impactful being able to share our work with them. And then I put up some resources here for you both to learn about PFAS in general and then to find out about your drinking water here in Madison. And so thank you all for your attention. I'm happy to take questions.
Thank you. There are a lot of similarities to PCBs, given the partition coefficients, volatilization, bioaccumulation, all that. So as a first cut for Lake Michigan, have you looked at the deposition areas for the PCBs out there in the Bay of Lake Michigan? Because the source areas, the source tributary loadings, I think when I look at your slides, are pretty similar to PCBs as far as Fox River and Peshtigo and the loading. So have you taken a look for where PCBs settled or found in both Lake Michigan and Green Bay as a kind of a first cut or thought?
Sort of, or not yet. I don't have the data for it yet. We were able to collect some, well, we didn't. Some very nice people from NOAA were doing a sediment survey in Green Bay this summer and pulled sediment samples for us. So we want to look at that. I'm not sure if we're going to see too much difference though. PCBs are really sticky. Like they don't really dissolve very well in water. So like once they're sort of in the sediment, they're going to kind of stay there. So they're going to be a little bit more localized than PFAS because they dissolve so freely in the water. They really do move around a lot. Looking at other data and past studies, some people have taken several samples around like Lake Ontario or Lake Superior. They don't find a lot of differences at different sites. They tend to be a little bit more evenly distributed. So they do behave a little bit differently than PCBs, but you're absolutely right. Some of the things that thinking about like bioaccumulation, those are factors that they share. So yeah, some similarities, but we can't just apply everything we know from PCBs to these chemicals because they do behave quite a bit differently. Yeah.
Is anyone doing this type of work for the rest of Lake Michigan?
Not that I'm aware of. No, there's a couple. One of the reasons why Lake Michigan doesn't have as much data is because a lot of the people who have worked on it up till now are based in Canada. And of course, that's the one Great Lake that doesn't border Canada. So there's a lot of good data in Superior, Erie, and Ontario. I don't know about the same scale quite in the good resolution, although now that I'm sort of talking, I'm remembering USGS is working on some studies like going around and doing, not so many tributaries, but some around all of the Great Lakes. So there's ongoing work going in some of the other places as well. Sorry, a little rambling. Yep.
You said there were about 5,000 of these chemicals. How are new ones discovered and who's keeping track?
Oh, that's such a good question. I mean, it's hard because, a lot of times like industry won't tell you, so you kind of have to guess. So some of them are new chemicals that are being made by industry. Some of the, I talked about the ones that don't degrade, like your PFOS and PFOA, but there are some that do undergo degradation reactions. And so some of the new ones that are found are just like, chemical A goes to B, goes to C, and eventually makes PFOA. So it's like some of these intermediates that are being formed and discovered. So there are different ways, like different chemical techniques for kind of just like looking to see what's there. And some of those approaches are discovering like chemical structures or different compounds, like new PFAS that we didn't know about. So there are different, chemical techniques doing like non-target analysis with like really fancy mass spectrometers where you can like kind of look and see what's there. But yeah, I don't know. It's a bit of a puzzle sometimes trying to figure it all out.
Is anybody keeping track of a database somewhere?
There probably is. I'm not sure though off the top of my head. But yeah, I just see, papers that come out every so often and the number is adjusted. So there must be people who have a big list somewhere.
Mark Schultz, online asks, what about PFAS regulation in Europe?
Yeah, so what about regulations in Europe? That's a great question. I'm not as familiar with what's going on over there in terms of like surface water regulations. I know there's, Europe in general tends to be a lot more cautious than us and follow sort of the precautionary principle. And I think they're probably a bit ahead of us, but I don't know off the top of my head exactly what the current state of regulations are there.
And China.
No idea. Yeah, it's a good question. I'll go look that up.
He also asked, in the equilibrium procedure, won't the PFAS stick to the plastic cap and why?
Oh, that's a great question. So if you, didn't hear it in the back, what happens like in your experiment, like with all these different things? You have to actually be really careful about what materials you use. So like for most organic chemicals, we use glass. Like glass is really great, but you can't use glass with PFAS because they stick to glass, or at least some of them do. So you have to use like very specific kinds of plastic that we've like tested and like people have tested and say work really well, but you have to be really careful. We actually had to, when we were sort of gearing up to analyze for these chemicals, change a bunch of components in our instrumentation. So we didn't have like background contamination and some of these issues there. Because we're working at really low levels, you have to be really careful. So yeah, that's a really great question.
So your nanogram per
Sorry.
liter concentrations in the water. If I understand correctly, that the sample was like 250 ml. And the reason I say that is like with PCB sampling we did back to get it to nanograms per liter. We had to take like 80 liters of surface water and run it through an XAD column to get it down. But are you really 250 milliliter sample?
Yep.
Yeah.
Yeah, our detection limits are like 0.4, 0.3 nanograms per liter. It's just the instrumentation is in the last like maybe 20 years or so has just improved so much that we can see things that low.
It's really doable to the water. You're not dealing with 8 liters anymore.
Yeah. Yeah, 20, this is plenty to deal with. Yeah, I know. I mean, we were hoping to go out on Lake Michigan. We were actually going to go last year and then the pandemic, and then we were going to go this year. And then the research vessel's engine broke down. So I don't forget it. But for Lake Michigan, where we were expecting things to be lower, we were going to get about 1 liter per site. But yeah, the analytical capabilities have really changed a lot. Recently. Sorry, Tom.
Comment, it should be added that the surface and groundwater standards mentioned are unlikely to be enacted in Wisconsin since they will be blocked by the state legislature.
Well, there's politics. Yes.
And then the next is, you showed the Fox River as a major loading source for Lake Michigan. Do you have any upstream data on the Fox River, such as near Neenah?
Nope, we only sampled at the mouth. So yeah, I don't. And I don't think the DNR has sampled the Fox for PFAS as far as I know. They did some like the Marinette River, they sampled at a few places upstream that I'm thinking of, but I don't think that's been done in the Fox. Yep.
How many years have you been working at this?
About 2. So it's pretty new for my group. Yeah, it's pretty new. Yeah, there's a lot. Everything that we do, we have more questions. I think there's a lot we still have to learn. Yep.
Okay, you mentioned about bioaccumulation in the body. Is there any specific areas that it targets, like organs, or just in general with that, so everything's not functioning as well?
Oh boy, this is a good toxicology question, which is definitely out of my wheelhouse a little bit. I'm not sure about humans. One thing this is again a contrast with PCBs. Some of these chemicals we think about going more to like fatty areas and things like that. And PFAS, it's more like proteins and lipids, like they don't follow the same behavior. But as far as exact like different organs and stuff like that, I think I would be guessing. That's a good question.
Online, one of the questions is, if the PFAS can be broken down, what would be done with the fluorine?
Yep, so if you break down the PFAS and you sort of get rid of the fluorine, it goes to fluoride. So that's the same thing as like, or similar to like chloride, like a salt. So when it's in its inorganic form and not bound to that carbon, it's not something you'd worry about anymore. It's the carbon fluorine concentration that's problematic.
Another person asks, where are we on banning PFAS? I'm assuming that's at the national level.
This is hard. Yeah, I mean, a lot of people are pushing for things like that, like getting rid of these chemicals or thinking about them as a whole class of chemicals. Different states are doing different things with like trying to move away from it, but I think we still have a ways to go with doing that. It's hard because they're used in so many things. So many consumer products, so many industrial applications. A lot of the things I talked about, like the sort of the hydrophobic, hydrophilic nature, like they make them really attractive and it's hard to replace them. So one idea that's been thrown out there is this idea of essential use. Weird. Only using them for things that we absolutely have to. But there are some steps being taken. Up until a couple years ago, like our fire department, a couple years ago, they phased out using PFAS containing firefighting foams. So like switching from ones that have PFAS to ones that don't, which is really good. So steps can be taken in sort of different areas, but I think we have a ways to go to get there for a complete ban.
Have you looked at health outcome statistics for different areas of Wisconsin with PFOA and PFOS?
I have not. I think there are some folks that are starting to think about doing that, but I haven't really seen anything on that specifically. Oh, sorry. Yeah, I was really echoey. Looking at any health outcomes, like differences in health outcomes around the state linked to these chemicals. Yeah.
Wasn't the Fox River dredge to get PCBs out of the sediments? And wouldn't that have reduced PFAS in sediment?
Yeah, probably at the time when it happened, but we have not really stopped adding these chemicals to our water. So we're, as we add more end up in the sediment again. So yeah, I think just focus, like with PCBs, a lot of times it's, thinking about like if you deal with the sediment, you're kind of dealing with a lot of the problem. But for PFAS, you have to think about the whole environment. It's everything. It's the water and the sediment. So it's a little bit more complicated.
And then if I'm reading this right, you sent this to the text, to the chat, so it must be somebody else. Is it absorbed through the skin when you are swimming?
No, it is not. So that is one happy news, is the main route that people are exposed is through ingestion. So either if you have like your drinking water source is contaminated, that would be one of the ways you would get PFAS into you, or if you're eating contaminated food, whether it's fish or like, I don't know, microwavable popcorn, stuff like that. But it doesn't go through your skin. So like showering and things like that or swimming wouldn't be as much of a concern.
And one last one from the chat. Raj is asking, can we introduce synthetic bacteria in rivers to feed on PFAS? And is it practical?
No, that's one's easy to answer. I think I've only seen one study where people saw biodegradation of some of these like really persistent compounds. And it was like really, really, really slow, like months sort of thing. So yeah, for like PFOS, PFOA, like biodegradation is not going to get us out of it, unfortunately. Works for other chemicals, but not these ones.
Any other?
Since you mentioned that you don't know the toxicity lifespan of these chemicals, are you primarily relying on the dilution principle in order to abate the toxicity levels? And
you mean for like sort of protecting like the environment?
exactly. I mean, it's just if you have more area, more space, whether it's water or land, you dilute the quantity of the chemical itself.
It's like,
I mean, I'm just trying to figure, are we doing anything other than trying to stop even the source now at this point, but to change the, we have a relatively cost-effective way to reduce the quantity of these chemicals.
Yeah, that's such an important question, is what do? We have this huge legacy. We find these chemicals everywhere. You know, I showed the Great Lakes, but they've been found all over the planet, like everywhere. I don't know that we know the answer, to be honest. There isn't a good, you know, destructive technology for getting rid of them. They last a super long time. I think thinking about preventing future contamination is really important. There's a lot of efforts on that, like in the state and other places, like to try to stop, to not make it any worse. But what do we do with this legacy? It's really, I don't think we know. It's kind of out there, and I mean, how do you clean up all the water in Lake Michigan? Like, that's not really a feasible sort of thing. So yeah, I don't have a good answer. I don't think anyone does. It's yeah, kind of one of the things that's really concerning about these chemicals is we're sort of stuck with this long-term legacy. We're going to be dealing with it for a long time. Someone ask me a question that's not going to be so depressing, please. Yeah.
I actually had one question. So this is just one class of chemicals. We literally have hundreds of thousands of chemicals that have daily lives. From what other drains that might be out there that could, other classes of chemicals that might be also from?
That's a great question. And I mean, yeah, this is something, because I mean, I don't just work on PFAS, I work on like pesticides and like other kind of crazy things too. There are a lot of chemicals out there. At some point, I kind of have to just be like, yeah, okay, we kind of can't deal with them all. I can't think of any chemical class that is as tricky as these ones. You know, they're getting a ton of attention in the media, research, I mean, good, lots of funding opportunities, right? But I think for good reason, because of some of the things that I talked about, just their persistence, their mobility, their toxicity at these low levels. I can't think of anything that's like, I think it's a good reason there are good reasons why they're getting so much attention, because I think these are some sort of the worst of the worst. You know, there's been other ones that have been sort of come up, and you know, like brominated flame retardants and things like that were getting a lot of attention a few years back, but I'm not seeing anything, at least that I'm aware of at the moment, that's like kind of has the same urgency behind it.
So maybe your upper question to finish, just to follow up on what this fellow said with and how they don't degrade. That was the story with the PCBs also. It depends on the content, of course, but they really didn't degrade. And I know what you're talking about, this chemical maybe dissolves a bit more. But with the PCBs, they looked at trying to destroy them. All of that just wasn't practical. But I think the Fox River was a fairly good success story, where in the end, it was a matter of taking the sediments, dewatering them almost to like a browning material, and then putting them in a contained area where they just weren't going to go anywhere. So that may be a partial solution too.
Yeah.
So the chemical wasn't destroyed, but it was put in a very manageable form and put away.
Yeah, I mean, I think one sort of more uplifting thing is just seeing how much action and attention and sort of urgency there is, you know, at the DNR and other places, or, you know, other states that are really focusing on this and like trying to come up with solutions. And just, I mean, every part of the DNR works on PFAS in some ways, like just seeing how much effort is going into it. I think that definitely makes me, I mean, yeah, people are working on it. So I think that is some reason for optimism, but we definitely have a ways to go.
Another question? Thank you very much.
Thank you all.